Hello and welcome to another episode of TWIML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. They say that time waits for no one, and that is also true of our discounted pricing for the upcoming TWIMLCon AI Platforms Conference. If you've been holding off on getting registered, you have until midnight tonight, that's Friday, September 6th, to take advantage of our early registration rate of $5.99. With your registration, you'll see my keynote interviews with industry luminaries like Andrew Ng. You'll get presentations and panels from presenters at great companies like Levi Strauss, Capital One, Twitter, Stitch Fix, Airbnb, NVIDIA, and a whole bunch more. And you'll get to meet and network with an amazing community of folks that includes our speakers, a bunch of former podcast guests that'll be in attendance, and your peers working at the cutting edge of building and enabling real-world enterprise machine learning and AI. To register, visit twimlcon.com/register. And while you're there, hit me up on the chat, where I'd be happy to answer any questions or provide an extra special podcast listener only discount for you. All right, on to the show. All right, everyone, I am on the line with Brian Burke. Brian is a senior analytics specialist at ESPN. Brian, welcome to This Week in Machine Learning and AI.
Hi, Sam. Thanks for having me.
Just as we started, you mentioned that you've been listening to the show for a couple of years. That being the case, you know that we speak to a lot of folks with really varied backgrounds on the show, but I think this may be the first time that we've ever talked to someone who started their career as a jet pilot, or at least no one's mentioned it thus far. How did you get from being a jet pilot to working in deep learning? I'd love to hear the story.
Yeah, sure. I left the Navy in around 2005 and did some work in the defense industry. After flying jets in the Navy off of carriers, what I was doing was pretty boring. I had a lot of spare, megahertz left over at the end of the day, and I was a big football fan. I noticed that the kind of the level of statistical analysis and common in the media was pretty lacking. I was pretty frustrated with it. I was like, the Navy had sent me to graduate school and put me through a program that was heavy in statistics. I had never used any of those, in my career in the Navy. But once I left, I said, why don't we use some of the stuff that, the military uses to win battles and wins wars to help win football games? And I was pretty ignorant of the Moneyball revolution and sabermetrics and Bill James. I was completely unaware of that stuff.
Okay.
So I was but that was a big advantage because a lot of the baseball people were looking at football research and they were trying to use that same cookie cutter on football, and it just didn't work. It's a very different kind of sport. I kind of had this military background. It was more appropriate way of looking at it. It was kind of two players, zero-sum game theory approach. And, kind of like we say in a dogfight, like, it's a knife fight in a phone booth. One guy's not going home that day. So that's kind of like a football game. It's football is probably the most, martial sport there is. So that's what the motivation was. So I had some software left over from, the trial period. It ended from grad school, and I was having a debate. I remember with a coworker of mine, and we were talking about, does defense win championships? And we were just going around in circles, just like most water cooler conversations like that. Mm-hmm. And I said, wait a minute, we can answer this. Let's just download the stats. I've got the software left over. We'll run a regression. We'll have an answer by the end of lunch. And I
love that.
Yeah, I just got hooked. And I was like, we can do more. Oh, we can predict games with this. We can do all these sorts of things. And so I really got in on the ground floor of football analytics, and a lot of the core models that are in use today throughout the league, that the teams use themselves. I was the developer of things like that. So expected points, win probability models, some of the core metrics that all came out of that period.
So a few years later, did you, is it still as easy as, hey, let's just run a quick regression on that, or did you learn from that initial experience that there's a lot more to it?
Well, that was it. I mean, I was mostly self-taught a lot of these modeling approaches, and the world has really changed since 2005.
Hmm.
Just the explosion of data and tools and modeling approaches, and so you have to learn them about as quickly as they come out. So and the paper we'll talk about today was no exception. I had to go teach myself neural networks just to kind of keep up with the state of the art.
Yeah, well, let's dive into that. You wrote a paper called DeepQB, Deep Learning with Player Tracking to Quantify Quarterback Decision-Making and Performance. Tell us a little bit about the background of that paper.
Well, at ESPN, we got access to player tracking data from the National Football League. So we have up to about 4 seasons worth of data now. We had about 2.5 at the time I did the paper. It's proprietary data. There are chips on each shoulder pad of each player in every game for every play. And so we have really accurate position, velocity, acceleration, orientation data at 10 hertz, 10 times per second. It updates. So, and it's almost real time too. So there's an API we can tap into. And so when we got access to this data, this was even before the teams had access. It was a lot. It was kind of the first true big data set that we had to wrestle with at ESPN on the sports side.
How long
have
those chips been in been available?
I think it's 2016. I think was the first full season they did it. Yeah, so I think we have 4 full seasons now, and it was. I think the first season was a little bit more of a trial, and the data is a little bit spotty, but 17, 18, 19, they've been improving it. So we got this data. We were like, well, we have to exploit it somehow. Let's get an advantage. What are we going to do? We came up with some pretty good ideas. Some of our best things aren't even kind of machine learning. It's just simple geometry. So we can analyze blocks, for example. Like in football,
before we do that, I'm trying to figure out the scale of this data in terms of number of teams by number of games by number of players by 10 measurements a second. Can you help us kind of think through or get a sense for how much data we're actually talking about here?
About one game would be about 4 gigabytes, I guess. So you can put
Wow.
one game at a time in your laptop and kind of chew on it. So that's kind of what I do.
Okay.
Yeah. So to span across games though, you have to really digest. I would say 80% of the effort on this project was just digesting the data and processing it in a way that was manageable for analysis.
You mentioned an API. Like, are you going and downloading all the data from a given game, or do you need to like collect it in real time or something like that?
No, it doesn't need to be collected in real time, although it could be. And we have been doing that for some spot analysis. So for Monday Night Football, for example.
Okay.
But we will. You can go back and get past games as well. So the system is called Next Gen Stats. That's the NFL's kind of brand for the stats. It's highly proprietary, but as a media partner of the NFL, we negotiated access, and so typically I think we download a play at a time.
Okay. And is the API or does the API allow you to download a specific play, or do you have to do like play segmentation on your own at the game level to figure out, when a play starts and when a play stops, or do they like code that when they're collecting the data?
No, they code that.
Okay.
They do an excellent job. I can't give them enough credit. So the certain events are tagged as well. So when the snap occurs, when the huddle breaks, when a tackle occurs, all these events are pre-tagged. So we don't have to do a lot of our own kind of tagging.
Okay. Okay, great. Yeah, so apologies for interrupting you. It was kind of curious about the data that you're working with. So you're saying that some of the things that you're working with, don't even require machine learning. You're able to do things just based on the geometry of is it the player formations that you're looking at from a geometry perspective?
Well, that's one thing you can do. Yeah. So, for example, one of the keys advantages to the Los Angeles Rams offense last year was they were doing a couple of things. They would sprint from their huddle straight to the line of scrimmage and snap the ball real quick, and that wouldn't give defenses times to kind of swap what we call strong and weak sides and do a lot of last second preparation before the ball snapped. The other thing they would do is compress their formations, very tight formations, which made it difficult for pass coverage players to play man-to-man defense. So that it forced the hand of the defenses. So just very simple things. We could just measure the time between the huddle break and when the ball is snapped for all the different teams and see which teams stand out and do analysis like that. That doesn't really require any sort of number crunching beyond simple, averages. Mm-hmm. Summary statistics, or the width of mean width of formations for different teams, and see how things stand out. My favorite thing so far has been something that's been a bit of a holy grail in football for a long time, which is stats for linemen. So much of football is kind of what we say in the trenches, and it's these the big guys who get no credit. You only hear their name when they mess up, but they do so much of the work to make teams successful. But there's no real statistic. Maybe for defensive pass rushers, there's sacks and some other things like that, but they're not very telling, or they're not very representative of overall performance. Mm-hmm. So what we did was we created a pass blocking and pass rushing metric that just looked at the geometry of the player. So I can tell who's blocking who. I can see who's being double teamed. I can see how long blocks are being held. So part of the problem in football is they're analyzing things the wrong way. You have to look at an offensive line as like a survival system. So it's like a systems engineering problem. It's kind of like a chain, right? And the first chain that breaks, the weakest link in that chain is the one that really matters. So we look at how long that system can survive and do analysis like that. And it's no more than, I know if you're very, very close to me and your shoulders are oriented to me, then you must be trying to block me. And if I get closer to the quarterback than you are, then I've won that block, or you're holding me. Either way, it's a win for me. So we can see how long those blocks are held. And we drew a line in the sand just to keep things simple at 2.5 seconds, which is the average time to throw, which is kind of the benchmark in the league for how long you have to sustain a block in a passing situation. And it's really taken off. We published like a first article about it on our website, and that afternoon we had NFL general managers calling, looking for full lists for all the players in the league.
Oh, wow. Yeah, one of the things that strikes me hearing your description of this that, is not all that dissimilar from the application of machine learning in a business type of context, traditional business type of context, is you're often needing to, define the problem, formulate the problem, define the metrics that are important. And it sounds like, I would have thought coming into this conversation that, we pretty well define the important, metrics in sports. Although, now that I'm saying that, that's, the whole thing with Moneyball was that we had all those metrics wrong, right? And it was really this, get on first base probability that, that hadn't really been looked at and kind of redefine the game. Have you figured out, is there that, one standout metric, kind of Moneyball metric in football? Have you figured that out yet? Or have you found several of these, like the blocking example you just gave?
Well, the blocking is really just an individual performance metric, which has been baseball is really unique, with the exception of cricket, in that it's really a simple sequential matchup problem between kind of pitcher and batter. And so you can isolate individual performance very, very easily in baseball. Football is a parallel system, right? There's 22 players on the field. There's 21 factorial interaction terms occurring between all the players. It's extremely chaotic. So we can't just run a regression on certain things. And different players have different roles, very specialized roles during plays, or very different kinds of plays. So that's part of the distinction between the sabermetrics guys trying to get into football. They couldn't really do that. The big breakthrough happened, I would say, in 2009, and I had just developed a win probability model. And I was really the first one that really worked, that didn't give you kind of junky, nonsense answers. And I was wondering what we can do with it. And so I thought this would be a really good decision analysis tool as far as the fourth down problem. So what to do on fourth down was this classic problem in football. You can punt, you can attempt a field goal, or you can try to go for it and keep the ball. And there was earlier research that said, well, you should be going for it a whole lot more often. Stop punting so frequently. I was a big believer in this research, but coaches were rejecting it because those models could not handle time and score. So depending on the time and score, you have different kind of risk tolerance. And that makes a huge difference, especially towards the end of the game. So we kind of went from Newtonian football analytics into relativity football analytics, when we could kind of adapt things for time and score. And once we were able to do that, it basically gave us a general theory of football decision making, and we could decide what to do on fourth down, know when to go for a 2-point conversion, when to call a timeout, any kind of game level decision that a coach needs to make. We can analyze it.
And so what allowed us to do that is that were there sounds like data driven models based on that, but was this machine learning, or was this some other kind of technique that allowed us to get there? And what was the before? How sophisticated was the use of analytics that in the theory that said that we were not passing enough?
Yeah, well, there was prior research by an economist named Romer, not the Nobel laureate, but another one. He looked at using what's called an expected points model, which takes into account kind of field position and the point value, the net expected point value of having the ball and having a first down at every single yard line on the field. And from that, you could deduce if you assume that the game is a point optimization contest for an infinite amount of time, then that model would apply. And that assumption of point maximization and infinite time works fairly well through the first 3 quarters of a game,
right? And
when the score is relatively close. But when a team is trailing by a lot of points, or well ahead by a lot of points, or in the end game in the fourth quarter when time is a big factor. So, for example, point maximization doesn't work if you're down by 1 point with 1 second left to play. You don't want to optimize your points. That might mean try for a touchdown. You just want to win the game. So going from point maximization to win probability maximization was this big jump. And yes, that was a big machine learning model. I was pretty new to all this. R was just kind of coming online. I had used SPSS in grad school, but what I wanted for my purposes didn't really exist. I wanted to use non-parametric regressions. And so I taught myself what's it called, the Excel basic plugin.
Okay.
I can't remember whatever that.
The Visual Basic for applications.
VBA for Excel. Yeah. And I created my own Lois function. Okay. And use that to build out the models. And the other thing is that football scoring happens in these chunks, like 7 points and 3 points, and so you can't regress over points. That they're discrete chunks. Being ahead by 2 points is not twice as good as being ahead by 1 point, for example.
You mentioned wanting to apply a non-parametric regression to this. Why non-parametric?
Because these curves were, you could use splined regressions. You could use it was very nonlinear. It was not something that they say, quadratics or polynomial type regression lines would adapt well to. So I wanted something more flexible, especially towards the end game. Things get very dynamic, and so these curves, these win probability curves, basically think of a chart of maybe the y-axis is win probability, the x-axis is field position, and we're looking at slices of time and score. And so basically you get a bunch of curves, and those curves are can get pretty dynamic toward the end game.
And so this was, did you say 2009 that the win probability model, you came out with that?
Yeah, I think I started working on that, and what I was able to do is acquire a big library of play-by-play data, and it was just this confluence of computing power and tools and the data became available online. So it was just kind of these things just all happened at the same time, and I just happened to have the spare time and the interest to tackle that. And yeah, so it was 2009, and I'll never forget. I had a brief 15 minutes of notoriety. The Patriots and Bill Belichick went for an infamous fourth down late in the game against Peyton Manning's Colts in 2009. It was November 2009. And I was already fairly established. I was writing for the New York Times and doing analysis for them. And I said, everybody thought that Bill Belichick going for it with a lead was a 4th and 2 on his own 36, something like that. And by the book, you always punt. And I wrote an article. I said, no, actually, here it was a good decision to go for it, even though it failed. And here's why. And it was just, once you build the models to apply them, it only requires a tiny bit of, algebra, and it's one line of algebra. And the next thing I know, Sports Illustrated was calling. ESPN did a big feature on me the next Sunday. Oh, wow. And so it was just by luck that this happened. And I think that got a lot of attention throughout the league, and teams started thinking about analytics at that point.
So I think we digressed a little bit from DeepQB. So you have all this data. Was DeepQB based on only the shoulder chip data, or are there other sources that you pulled into that model?
Well, we used some of the metadata from the play itself, so down distance, yard line, and we also collect by hand at ESPN. We call it video analysis tracking, and we have a human person looking at each play in near real time, and they'll say, was this play action pass, or was this a drop? So it was a good pass. It landed right in the receiver's hands, and he should have caught it, but you just didn't make the play. So little things like that was added to the player tracking data.
Got it. And I think we skipped past the punchline. What's the key problem that you're trying to solve or answer that you're trying to get at with DeepQB?
Well, I was interested in quarterback decision-making. That's probably the most mysterious yet most important part of football, especially in the NFL, where it's really a passing game, and the quarterback is so important. And that decision making, you can analyze physical skills, right, like running and jumping and strength and things like that, but it's really hard to quantify decision making, especially under pressure in highly dangerous situations. So it reminded me of my days as a fighter pilot. I wasn't the athlete that Cam Newton is, but when I strapped an F-18 on my back, we were all Cam Newtons out there, and we all had to make kind of life and death decisions under great duress, right, and under uncertainty as well. And so I saw the parallels. I was very interested in that, and so I thought, okay, how would we examine quarterback decision making?
And so tell us about the model that you came up with to do that.
Well, what I wanted to do was use a model to try to predict which quarterbacks or which receiver of the 5 eligible receivers a quarterback would throw to. And the idea was that I wanted to identify quarterbacks who are making good reads and identifying the best receiver to throw to. So this is a decision he has to make. He has to choose between 1 and 5 to try to throw to. And that's the key decision I wanted to look at. So what the model was trying to do was trying to look at the play itself, look at the presentation, the geometry, the velocities, the positions of all the players on the field, and say who should an NFL quarterback throw to given this picture presented to the quarterback. The idea was, it was kind of epistemological sleight of hand. I was like, well, these quarterbacks are all really, really good. They're the best in the world. So the average typical quarterback is probably making the right decision. And therefore I'm going to compare each individual quarterback's performance, which receiver he does throw to, with what the model suggests the best receiver to throw to would be. And so that was the idea.
And did your data include characteristics of the receiver, or is it solely based on the play geometry and the options available from a field position perspective, as opposed to the some kind of data talking about the receiver's performance historically in that kind of situation?
No, unfortunately, no. There's really no the data has no Z axis to it. So there's no, we don't know how high he jumps or how high the ball was thrown, or we don't know that. We do know things about the receiver as far as what's his velocities and accelerations and things like that, which his individual talents certainly are big influences on. So, but what we don't have is the hands. Some receivers just have better hands. They just have a knack for catching balls. So unfortunately, no. But we're aggregating over a large, very large data set. So the idea there is that it's going to average out.
So you create this model that is trained on the historical decisions that quarterbacks make, again, with this assumption that they're all good quarterbacks. And then you want to be able to compare any given quarterback decision with this model to see if it was, a good decision, or maybe the quarterback kind of, made a bad decision under pressure or something. That's the general idea.
Yeah. So the idea is to isolate the contribution of quarterback decision-making to performance. So we can observe the performance on the field. We see, okay, that was a 10-yard catch, or that was incomplete pass, for example. How much was the quarterback decision contributing to success and failure in these plays? So I was thinking of a quarterback. If you're a football fan, you may be familiar with a quarterback named Tyrod Taylor, who's infamous for overlooking open receivers. And instead of throwing to an open receiver, he was a little bit gun shy. He would take off running. He was a very fast runner. And he was not a bad quarterback, but coaches were very frustrated with him for that. And so I thought, can we identify something like this? Who's making good reads and who's making poor reads? And so let's say in the case of Tyrod Taylor, there is a receiver that's open. The model sees it. It says, hey, a typical NFL quarterback would throw to this receiver 80% of the time. Tyrod is throwing to some, running back who's, 2 yards deep instead, who the model doesn't think he should throw to. And then we would use those comparisons to make a judgment about quarterback decision-making abilities.
Yeah. Does the model also work the other way? Meaning, can it identify quarterbacks that are able to, have a higher than normal success percentage throwing to unlikely receivers or something like that?
Yeah, absolutely. And in fact, that's what happened. So the assumption about the kind of, hand waving I mentioned earlier wasn't really true. And so what happens is, you want to say hey, Aaron Rodgers is a really good quarterback. He makes good reads. Do what Aaron Rodgers would do. Just make the same decision he would make. And you would tell a rookie to do that. But that would be calamitous because that rookie doesn't have the same skills, the same accuracies, the same arm strength necessarily as Aaron Rodgers. So Aaron Rodgers is making different reads, making more aggressive reads than, say, a typical quarterback because he can, right? There's a selection effect. And so, the insight is in the difference, from the predicted. So the model is just there to establish a baseline. And then what's interesting are the deviations from the baseline.
Right. In both directions, it sounds like.
Yeah.
Tell us more about this model. What kind of model is it?
It's a neural network, very vanilla. It's just a feed forward network. I was really just getting started, and I just wanted something that would work. So there's some other different kinds of models you could use. Some of the previous work in soccer and basketball would take the player tracking data, kind of create a graphical image of player trajectories from that, and then use convolutional neural networks or LSTM type recurrent neural networks. Mm-hmm. I just took a snapshot in time at pass release and looked at the play, and looked at where the receivers were, where the defenders were, all the relative geometries and velocities, and built a I think it's a 4-layer feed forward network. And at the end of it, you could ask it just about any question. So it was kind of modular, I would say. Tell me, like we've been talking about until now, predict which of the 5 receivers you think this quarterback should throw to. Mm-hmm. Or I could predict the mean yardage gained you see on this play, or predict whether or not this is going to be intercepted or not, or completed or incomplete. So you could ask the model the same question. And what really surprised me was that when I was going through and kind of tuning all the hyperparameters, all the number of nodes and layers and things like that, it was really the results were invariant to that structure. Or the structure was really dependent on the data. And since I was feeding it the same data but asking it different questions, I could keep the same network structure and just kind of change the final layer and get very good results.
The network was relatively straightforward. You mentioned R earlier. Did you end up doing this in R or something else?
Yeah, well, it's a plugin through Python, but I thought
you were going to say an Excel plugin.
Yeah, no, I've graduated from those days. I'm an R cripple. I mean, I'm fluent in R, but I can probably order dinner in Python. But that's about it. But there's a great plugin through R. And since I was doing all the data building and processing through R, it was very handy just to stay in that environment. Okay. So yeah, Keras with TensorFlow on the back end, and it converged and started giving me results. I was very surprised. My first try, I was very excited when I started getting good results.
We talked a little bit about the structure of this data. You've got kind of games that are aggregates of plays, and then you've got, 4 years worth of games. How much of this data did you use to train on, and did you find that, how much of it kind of got you to the point of diminishing returns?
Well, I used all the data I could. I didn't really try to find out how little data I needed. Uh-huh. So I was using, I split the data into 3 parts. So, training, validation, and then test. Mm-hmm. And the test was set aside as just the current season at the time. So when I was writing up the paper, so that was the 2018 season. So I've got about 3/4 of that 2018 season is kind of a test set. Mm-hmm. Then all the training and validation, all the tweaking and things, that was done using like about a 70-30 split of the 2 seasons of 2016 and 17, I suppose. Mm-hmm. And then that was useful because the test results, right, which hadn't touched any of the training or validation data, had never been seen by the model in any form. That was the current season, so we could do actual analysis, like real world analysis, using the test results.
is the model trained on a play at a time, or and is it trained? I'm assuming it's trained on only passing plays, so you're filtering that out based on these tags, and you're training it on a play at a time, or is there some other structure for the training data?
Yeah, it's only passing plays, and in fact, it's only targeted passing plays. So any plays that were kind of throwaway.
Got it.
Throwaway. So quarterback just didn't want to get sacked, so he throws it out of bounds.
Yeah.
Those were discarded. So there was no target on this. I couldn't predict what the target was. Theoretically, you could make that a sixth option. I in retrospect, but that wasn't really what I was interested in at the time.
Yeah. Yeah.
And then, so it's trained to, basically a play, the atom of this model is one play. Right. But there was a batch of plays that obviously that was fed through,
sure.
for the training.
And how many plays total did you have access to in your data set?
I think about a little bit foggy, but totally about 36,000.
Wow. Okay.
Pass plays.
Yeah.
And which I think is more than sufficient. But I also I did this trick where I just took the mirror image of every play and added that to the data. You have to be careful not to have the mirror image be both in the validation or training, right? So you have to segregate those, but that way you're getting even more data with the assumption that there's symmetry to a play. So somebody who's wide open on the right side of the field would be just as wide open on the left side of the field. And that's generally true, except for quarterback handedness. You can have right-handed quarterbacks, left-handed quarterbacks that might have an effect. But there happens to be no left-handed quarterbacks for the last few years. So,
okay. That's an interesting approach to data augmentation. So when you do that mirroring, given the handedness of the quarterbacks, are you just mirroring the line structure? I guess the quarterback is just a point here, so that doesn't matter, right?
Yeah, you just like I was, I just picked up this common technique with, computer vision techniques, right? So you want to identify a picture of a dog, that the dog kind of looking to the right. If you flip that image with a dog looking to the left, they're both dogs.
Right.
So that was the idea. But it's complicated. Like I had to do it by hand essentially. So I had to, do all these kind of geometric transformations, including with all the angles as well. So if you're heading 0-3-0 on the true play, on the mirrored play, you're heading 3-3-0.
Right.
So it was a little bit laborious, but it was in the interest of eking up the performance metric by 1 or 2 points.
Okay. And you mentioned that you segregated your validation and test sets based on the season. Did you explore, something that was more randomized, or any kind of implications of kind of bias season to season, like over long-term periods of time, players get, better and stronger? Does that have any effect in a short-term season to season?
Well, yeah. I didn't do that, but it is well known that quarterbacks take a jump after their rookie year. So they're from their second year on is kind of their steady state performance level. So if you really want to know, like what is this quarterback's career going to look like, with very rare exceptions, his second full season is very representative of, he's pretty much hit his steady state at that point. So, but no, so because we aggregated the idea at first anyway. There's a fourth variant of the model I haven't talked about, but there's it's basically the aggregation, the average quarterback all kind of blended into one, was kind of like the proto DeepQB.
Okay. And so you kind of ignored the, any implications of testing based on a totally separate season as opposed to kind of randomized testing.
We did find that the 2018 performance was where there was a drop in performance like you would typically expect. But there was an unusually high number of rookies. It was generally an up year for passing. So there's year to year variance due to things like just randomness, rule changes, injuries to some of the elite quarterbacks will change overall the level of passing performance for the league as a whole, year to year. Last year was a big up year. So yeah, there might be something to that.
You mentioned a fourth variant to the model.
Yeah, this was the coolest one, but it didn't work as well as I had hoped. But I thought the idea was so cool, I had to put it in the paper anyway. People were like, "Yeah, that's too long your paper, so you got to cut it out, cut this part out." And I was like, "No, it's too cool." So the idea was to use transfer learning. So it's kind of inspired by the same way, let's say, biological brains work. So think of quarterback has to have these very intuitive, instinctive parts of his brain that understand things like distance and motion and speeds and this kind of intuitive physics model in our brains. And we generally share those, right? We're all pretty good drivers, right? We're all humans have these faculties, but we don't all have the same decision making. I have an 18-year-old son, so I know we don't all share the same decision. He's a very good decision maker, actually, for an 18-year-old. But I was 18 once too, so we don't all share the same decision making abilities. So those executive functions may tend to differ much more than the lower level functions, and those are you could model it the same way with neural networks. So what I did was trained the lower level layers of the model on the data set as a whole, just like I had done with that we've been talking about. Mm-hmm. And then what I would do is take the top layers, which we could think of as the executive functions, the ones that are, okay, we've digested this play, we understand where people are and what's important to look at and the relative velocities and things like that. Yeah. Now let's make a decision about who to throw to. And so those top layers, we froze the base layers, retrain the top layers just on an individual quarterback. Mm-hmm. And then we could say, we could take like a Tom Brady, or like I did within paper, I took Drew Brees, and you could basically download Drew Brees' brain into a USB drive or something like that. It would be the idea. Right. And then just like we said before, like do what Aaron Rodgers would do, right? So we have a model of what Aaron Rodgers would do or what Drew Brees would do given certain situations. So we could actually take a situation that Tom Brady was in and replace him with a rookie and say, now, what would the rookie do compared to Tom Brady in this same exact situation? Mm-hmm. It was pretty ambitious. The results weren't as interesting as I thought, partially because the rookies tend to throw a lot of checkdowns, which means they throw short passes to relatively safe receivers rather than taking a lot of risks. And the Saints offense happens to do that by design a lot. They have very good running backs last year. And so Drew Brees came up. So we ran a similarity metrics, and all the rookies came up very similar to Drew Brees, which is not what I had hoped to see.
And was that the only quarterback you tried to apply it to, or did you apply it to all of them and you found that it was kind of similarly not all that interesting for all of them?
Yeah, well, I tried some of the consensus elite quarterbacks, so Brady's, Rodgers, Brees, and I can't remember if I did with anyone else, but I chose Brees. The results were decent with him, and so researcher's prerogative. That's the one I put in the paper.
Interesting. Yeah, that would have been really interesting if it worked.
Yeah, but it was just the first stab. I mean, really, This is the first research like this is beyond this is commonplace in basketball and soccer, but this was just the first stab at it with football. We were just kind of like, let's take a moonshot here. If we could do something, the coolest thing we want to do, go run with it and see how far you can carry the ball.
What are your priorities for kind of pushing this further? Do you use a relatively simple model? Do you think kind of a deeper, state-of-the-art CNN might perform better, or, doing different things with the data and, finding additional data sources to kind of supplement what you already have? Like, what do you have in mind for pushing this further?
Well, the next step would be something that we could run this. First, let me say we can run this model at any kind of time step in the play, well before the pass actually takes place. And so we can have a continuous analysis as the play goes on. But it's only trained on when the pass is actually released. The next step I would do if I had the time would apply LSTM models to the data.
Okay.
Throughout the so it would be continuous from the snap all the way through pass release. And so we're accumulating information from the entire play, not just a time sliver at pass release. But do keep in mind, we do have velocity and acceleration information on each player, which kind of gives us, back, 2 time steps, I guess, in theory, worth of information. But I think we can accumulate even more information. I don't think CNNs would perform as well in theory, because what the CNNs are trying to do is to get position and get the geometries, get the relative information from a graphic, and then you apply that further downstream in a model. Whereas we'd already have the X's and Y's and the distances and geometries and angles that a CNN would have to learn along the way. So we can. So I think using the raw inputs, the X, Y's, the distances, some features that are engineered, kind of relative distances to nearest pass coverage player, things like that, I think would perform best.
I'm curious to the extent to which explainability has come up for you. Do you get asked to be able to produce some justification for the predictions that the model is making, and how have you handled that?
Yeah, that's a tough question. Sometimes there's some head scratching results. You don't under why is the model saying that, and most of the time though it's very understandable and plausible, kind of obvious. But on a case by case basis, you can look at these plays and make a human judgment. And if you know enough football, you understand why it's making the decision it is. The model's working the way it is. But unfortunately, explainability is a tough problem with neural networks. Mm-hmm. If I had the time, what I would do is I'd build like an application where you could kind of dial in. You could just drag and drop players on a screen. And some of the Disney research guys I talked to had actually done this with basketball, where you could kind of move the players around and then see how that affects the model outputs. And that way you can directly test, well, if I make this player closer to this other player, how does that affect things? If I make them further away, if I make them faster, how does that? So just by trial and error, you can come to some form of understanding, but some general understanding about it is a difficult task.
Awesome project. What suggestions would you have for folks that are listening to this, also have a passion for sports and want to experiment with these types of models applied to sports?
Well, there is player tracking data available, even for football, even for NFL football. But there are databases out there, some soccer. Basketball is a little bit harder to get a hold of. I can't give you any, I don't have a URL for you right now, but except in football. So the NFL at the combine in the spring, late winter, early spring, at the combine, they held what they called a big data bowl. And with that, they released a subset of games, I think maybe about 9 weeks worth of games. And they released that data for a basically Kaggle type competition. Mm-hmm. And then they had their winners and their finalists and announced a winner there at the combine. So that data still exists out there on the web somewhere. So just Google big NFL big data bowl, mm-hmm. And it'll take you to that site. And I think it's still available. There are definite limitations on what you can do with that data. The other thing is the NFL put out punt play data in Kaggle, and that may still be available as well. So if you're interested, that's a great place to get started, just with the data. But it's a lot to get your arms around. You have to start, learning like, okay, the 0-0 point, where is that on the field? Is that at the back of the end zone? Is that is this left oriented, right oriented? Is it, which way is the 0 degree heading axis on here? And is this in degrees or radian? All those things, that takes a while. So it's definitely a chore, but it was a lot of fun.
Well, Brian, thanks so much for taking the time to chat with us. Really, really interesting stuff.
Yeah, thanks for having me on, Sam.
All right, everyone, that's our show for today. For more information on Brian or any of our guests, visit TWIMLAI.com. Be sure to register for TWIMLcom AI platforms right now before prices go up tonight. As always, thanks so much for listening, and catch you next time.